So shall we start? Hi, everybody. Few updates. One thing regarding the project, some of you have asked already on Piazza. So yeah, I have made the agreement. I mean, I could book one room. So it's going to be on the second week of December. So based on the schedule that I see, we are going to finish on December 3rd. Then the fifth one is not included in the course unless the first session was lying on one of the holidays, so I could use it as a backup. I can use it as a backup, yeah, so if the course was not over, but I think we don't need it really. So then the next week we're going to have same times, but another place, so it's going to be BL building. I'm going to send you the exact place, so we're going to have the seminar there. So this is the point regarding the final project. So for the final project, as I told you, I don't want you to have a presentation. It's going to be a poster session. But the poster session is because we are too many people, and it's hard to just ask everybody like moving around. So it's going to be like a very short you're going to show up your poster in some sort of projector, I mean, on the wall, and then you're going to explain like very shortly, up to maximum 5 minutes, what is going on in your project, what you have seen, what was the result, and things like that, okay? And then there are going to be 1 or 2 minutes of questions, so you should expect some question from your own supervisor, definitely, but it might be that the other students or me also ask questions, okay? So this is regarding the final presentation. Some of you, I do know, this is close to the end of the year, so some of you might have travel plans. So in that case, it's no problem. Just let me know in advance. You can submit, I mean, you can record your video and submit it online. And then I would watch your video, and then I just do the marking based on your video, okay? In case that you could not attend, like you are really traveling before December 10th. If you want to have a specific date, like December 10th, December 12th again, are the days. So if you want a specific day, like you would say I have exam or something, it's again okay, just let me know in advance, and then I try to schedule that you do the presentation on that day. And one thing else, that everybody is supposed to attend unless you could prove that you cannot attend, okay? So because this is it's like the final exam of your course. So that's it. Yeah, you got a question?
Yeah, well, what time is it?
Exact same time, 6 to 8. So your course time, only we have another place, okay? So I could do it like earlier, but I was afraid like people have something to do. So this is the course time. Usually people don't have anything to do at that time. Yeah. Yeah.
I have another course on the final from 3 to 6.
Which day is it?
Like same day, 3 to 6.
Yeah, but which of the, because we have 2 days, Tuesday and Thursday.
Tuesday.
On Tuesday, okay. Just write me an email, then we're going to do it on Thursday for you.
December 12th is also...
Yeah, 10th and 12th, because there are 43 groups, so definitely we cannot do it in one shot. Okay. So they're going to be 2 days. If you cannot attend one of them, you have exam, just let me know. Yeah, I'm going to put announcement to everybody, but just you get it first hand before everybody who attends. Yeah.
Just to show the poster is just like one slide, I guess.
Yeah, one poster. Yeah, exactly. The one which you print, but you don't need to print it anymore. You just show it up here, and everybody listens. Right? Yeah.
So no slides?
Sorry?
But that means we cannot do a slide.
No, don't do a slides, because posts are going to be easier because you are just talking like 3 to 5 minutes, right? And then, I mean, that's going to be much easier to follow as compared to slides, because then somebody would say, okay, go to slide number 2. And, yeah. Unless you really need something, like you want to show some demo or something. Not demo, I mean, you can still show it. But if you want to, for example, have some animation or something like that, then maybe you do it 2 slides, 3 slides. But just let me know. It's not our thing is just to do a poster, okay? Yeah.
Are you gonna have like one presentation with everyone's poster?
Or we have to plug in every time. You know what I mean?
No, you send me, and then I put it like in order, and then you just come over. So we're gonna schedule it ahead of time so that you do it fast. But yeah, you just go there and you have your poster, and then you can talk.
And how long?
3 to 5 minutes. I'm gonna write it down explicitly, like what exactly we're planning to do. But 3 to 5 minutes roughly would be the time, right? Okay. So any question you might have? Cool, great. So then let's go for the for recurrent neural network. So last time we got to know what is RNN, right? And what was RNN? It was basically one neural network that we had. We just make it recurrent, meaning that we get the output, we get out of the higher layer something, some hidden kind of information, and then we feed it back to the input of our neural network for the next time. And then it helps us to somehow track the memory through our input sequence, right? So we talked about this issue that there are two main challenges when we get into RNN. The first one was the question, what should be the memory component, right? So what should we choose as that state that we came up with? Because we wanted to just capture the memory within a finite size, but somehow infinitely over time. And the only, or not the only, but the main key idea that we came up with was the use of state-dependent models, right? Space-space models. And those models are simply models that they have state, which is getting updated every time, and then we use that state to compute our output. So the first question when it comes to RNN was that how we can specify or state, cite that this is a kind of useful state, or somehow learnable state. This is the first thing. The second thing was that how we can learn the memory through time, right? And we talked about the two basic approaches. One of them was the Jordan approach, which you took the output, just computed the moving average of that and consider that as a state. So like this depends on the time. Like each time I'm getting the output of that time or the moving average of that and feed it back to my model for the next time. So this was a kind of state-dependent model, but this didn't work well. And the key idea, the key issue was that you could not really learn that memory because you're basically enforcing your output to be the thing that you want, yeah, your label. So then the L-man idea was to just take the hidden features, the output of the hidden layer, to be your state. And it was a better idea because your hidden features are not supposed to be something specific, right? They don't need to be something very specific. They could be anything, and you could potentially learn the memory. The second challenge was how we can get back over time. And we started to write down the back propagation because at the end of the day, we're going to have a bunch of weights. For example, in this architecture that you see, this is the L-man architecture. We have three different set of weights, right? So the first set is this blue link here, which is connecting the input to the hidden layer, right? So it was a matrix, a bunch of weights, correct? Getting multiplied with the input, and then you add it up with another set of weights. So you have another set of weights here on this horizontal line, and this guy is going to get, this matrix of weight is going to get multiplied with your previous hidden feature, and that adds up to that guy, correct? So two sets of weights, and the last set of weight is the next link here, which is going to multiply the activated version of that thing, and then just multiply it with the weight, and then again you activate it, you compute your output, right? And then we said each time that we go, when we pass through time, if you want to train this model, each time, at each particular time that we look at the output and we try to change the weights, we are basically changing also the weights that impacted every time before, right? Because it's very important for you to remember always, this is one neural network, right? This is a neural network. I'm passing it through time, meaning that the blue line here is the same everywhere. Now, if I get into that time and I change that weight, this means that everything before gets changed, correct? So if I made my neural network at this particular time to give me at the output, I don't know, the word pet, once I go further and I change that weight, then there is no guarantee that I get pet in the previous time anymore, right? Because I have updated the weights. Clear? So now if you wanted to just backpropagate, such that we just minimize the whole loss over time, how could we do it? We had to backpropagate all the way back to the beginning of time every single time that we want to compute that gradient. Meaning that starting, say, I am just computing the loss at this particular time, then I want to get, or I want to update based on this guy. I just want to update the weights inside my neural network. It's not enough that I get back to this point and I stop. Yeah, this is not the same thing as we had before. I need to just move backward all the way. I need to, when I get here, you remember we saw in all of those chain rules, some extra terms pop up, and then we need to just move backward 1 time a step, 2 time a step, so on, until I get to this point, and then at this point I'm going to stop, right? And then at that point, I can really compute that gradient, and I can update my weights. And potentially, if my sequence is very long, it's going to be a very, very long or deep backpropagation through time. Clear? So this was this other issue. So as I told you, Ellman actually did not do this. So what Ellman did, he came up to this point, and then here, when he wanted to go backward, he just assumed that the impact that is going to be after this is going to be negligible. And as you're going to see, it's not really negligible. It doesn't mean that it's not numerically negligible, numerically small. It could be numerically small, but this is basically the main thing that helps you to just train over time. Okay? So that was the issue that Ellman did. So he did not really learn the memory through time. He just get a kind of very poor approximation. And at the end of the day, he saw better performance as compared to Jordan model, but it was still not promising. So this is why people stop on working on such models at that point of time. At that point of time, backpropagation was not a big thing. So yeah, many people started. So this is what Ellman did. So he came here, he stopped, and then he just updated the weights. And was not really doing the job. So now I think we talked about this, right? So the memory component was rather simple in the models by Ellman and Jordan, and also they did not, none of them could really train the model through time. Now, this is the point where people started, as I told you, think that these guys are not going to work, up to the point when people started to deal with, neural networks, really deep neural networks started to work for simple, classification problems. And some people started to think maybe we could get back to those models. It doesn't mean that nobody works on it, like in this period of time, but it was not a hot topic at that point, okay? And then, at that point, the people started to believe, okay, if we're going to improve the model, everything is going to, at some point, work. And now we do know how to do backpropagation properly, so maybe we can make it work. It started to work, but they actually need at the very end to use the idea of gating, which is an old idea, but they could reinvent it once again. So now, at this point, I just want to define for you the RNN. So RNN is, as I told you, any architecture that you had before with only this particular difference, that you're going to learn your output not only from the features that you have at that particular part of time, but you are going to just use the features that you had from other time instance. And this term recurrence comes simply from the fact that you're using the features of the previous times, okay? So it doesn't mean that you cannot come up with an RNN which uses, like Jordan, the output, but usually we just use the hidden features, yeah? And the main reason is simply because we want to learn that memory, okay? So that's it. Now, let's start with the idea of RNN when we want to just do a supervised learning task, which is the main topic of this course. As I told you, this guy is some sort of, starting point of the transformers and many things that we have in sec-to-sec modeling. And this is one of the one of the key components that we started to do unsupervised learning with, because as we're going to see in the next chapter, we can simply use a simple RNN, and then we can just make a kind of basic language model, which starts to give us coherent sentences, right? And at that point of the time, we don't have any more supervised learning problem, right? We do have unsupervised. So I would just want to have a coherent sentence, right? But for the moment, we are just focusing on this supervised learning problem. And the key factor in this architecture when we deal with supervised learning is that we want to just learn the label of, say, one particular time instant from a sequence of data which has potentially temporal coherence. And what do I mean by temporal coherence? I think most of you do know it. I used it a couple of times. But simply by temporal correlation, I mean that one particular instant in your sequence, xt, is not independent in its own information. So the information of xt is potentially available at other time instants as well, right? When I say a sentence, Ali is a good guy, and you dare doubt it. Yeah. So Ali is a good guy. I mean, after good and Ali, you need to have something related to me, right? So it should be a guy. So that term guy also contains some sort of information from the previous words that we had in the sentence, right? So this is the temporal correlation. And one thing at this point that I want to mention to you, there is one issue here that I just want to bold it right now, then we leave it, and then somewhere at the very end of the chapter we're going to get back to it. And that is the point showing up here. We don't have it in previous cases. The issue by assigning the labels into the output of our neural network, RNN. So what is that issue? Actually, in practice, okay, you might when we started initially to talk about it, like on Tuesday, we always thought of the RNN to be of this form, right? So we thought that I have one sequence, say of length 10, and then for every time instant, I'm computing one output. So I'm going to have one sequence of length 10 as well at the output. And every single guy there has a label, right? So this is what we consider like it's the most simple case we can think of. So for example, say we have speech tagging. So you have a sequence of words, and then you just want to specify what kind of role that particular word has in the sentence, right? This is now, I don't know, this is subject, this is verb, this is that. So you want to just specify. So for every frame, you have one label, correct? And then if you want to train such a model, basically you have your outputs, and you're going to just write your labels next to them, and you can simply compute the loss, right? That is not an issue. This is the first type of the sequence-to-sequence transforms that we could have, and we call it many-to-many. Simply means that we have many inputs and we have many outputs, right? And this many-to-many, it could be one-to-one connection, correspondence, as we have here, right? But we could have another type of many-to-many transform. So I could have one sentence, for example, when we are doing a speech recognition, right? So I could have one audio, and then I want to just look at it, and then, for example, on YouTube, you have the same thing, right? You give a video, and the video, you could write an algorithm which just cut your video into parts and say, this is the first section of the whole video, second section, the third section, right? And each of them has one label, correct? Or when I speak, you might say, okay, he's speaking 2 hours, but the first part was for section 1, the second part was for section 2, and the last part was for section 3, right? And then you want to just recognize each part of this speech and then label it. So this means that you could have a very long sequence, and at some point you're going to say, okay, this is the end of first part. Then you're going to have a lot of other things. This is the end of the second part, and so on, right? So still you have many inputs, you have many outputs, but there is no one-to-one correspondence anymore. Clear? Yeah? Now, you could have potentially labels inside your data set, because I have a sequence at the input. So this is the whole speech video file, the speech audio. And then I could have the labels as well. So I'm going to listen to it, and then I see, okay, at time instant 10.0.1, this is the end of part 1. So I'm going to label it manually part 1, right? So I'm going to have V of this time, I'm going to have V of this one in my data set, correct? But I don't have anything for any other time instant, yeah? And it could come to be a trouble, yeah? We're going to get rid of it at the last section of this chapter, okay? So this is one other case. Another case could be that you do have actually some instances that you don't have any input anymore, right? What could it be, for example, language translation, yeah? This is a very typical scenario I mean, we're going to do it next chapter for a basic translator. And then this is a typical thing in that situation. Like if your input is a German sentence, usually in German this verb comes at the end of the sentence. And if you want to write down the English version, you just need to wait till the sentence is over and you start to write it down at the other side, right? So you pretty much have no label at this point of time because the sentence is not yet over, right? You just start to have your labels at this part. And there is no reason that the output sentence is of the same length as the input, right? So you could have a very long German sentence and then it's translated into much shorter English sentence, right? So no one-to-one correspondence anymore, no time alignment even anymore, right? It's still a many-to-many model or kind of problem, but it's another type again. Clear? And of course, you could also have one-to-many problem and many-to-one problem. One-to-many problem means that you have one input at the first time instant, and then you just want to generate output, right, for a long time. The example, simply image captioning, right? You just look at the input. So this X1 is one image, one tensor, RGB image. You give it to your machine, and you want your machine to just write down a sequence, which is the caption of that image. Image of a tree in a landscape within, I don't know, in Iceland, yeah? So you want it to just write down a long sentence, but you have one-shot input, right? So again, here you don't have really one-to-one correspondence. Clear? But of course, I mean, in this case, you might have some benchmark, like you have in your data set, you have one image with multiple, captions for it, and you can put it, but those captions could be of different lengths, right? This is another case, and as I said, the other thing is that you have, for example, many inputs and you have just one output, right? This is again a kind of classical thing could happen. For example, you want to just classify one sequence, right? The example that we started with, you have the whole speech, and then at the end you want to say whether it is about sport or science, right? So you're going to wait till the end of the whole sequence, and then you're going to give only one output, right? Yes.
How can we define this cost function for this kind?
Yeah, this is the issue that I wanted to mention. So these problems are quite challenging. So this is what we're going to do at the very end. This is what we call it one-to-one correspondence problem. So meaning that the output that you have, because like, for example, even in this case, it's true that I am not showing any output here, but I do have the hidden states here, right? Hidden output of the hidden layer here. And I could potentially compute those outputs, right? And those outputs, of course, they are not the label that I want, but they carry some sort of information. But then the question is that how I can measure their contribution into the loss. Yeah? And this is the problem of one-to-one correspondence. We're going to talk about this, okay? Potentially, you can, like naive approach, you can just copy the true label everywhere in time, right? And you want it to be very smart, just start to classify at the very beginning, right? This is a naive approach, but you can do it, right? Okay. Everybody's clear? Good. So we do have these different types of problems, and this is just a one short note that whatever we have studied up to this point were actually special cases of this, more general sequence type problems. Because what we can say about like FNN, the MLP or CNN, we could think of one-to-one RNN, right? We have input whose one sequence of inputs, which is of length 1, and then the sequence of labels, which is 1, again, right? Correct? And then this is one very basic case of the more general case with RNN, right? So this is somehow covering everything before. So if I was a bad guy, I could start from this point, right? And I say, like, we study this, then you learn everything else. But obviously, this is not going to work, right? So this is one way to look at it. Another way that we can look at everything that we had before is that we just take the whole data set, for example, and then we put every single input next to each other, and then we put the outputs, the labels also as the outputs next to each other, right? Then we're going to think of our data set as one sequence, but the entries of the sequence have no temporal correlation. Clear? Yeah? And here, we don't have any sort of one-to-one correspondence problem, because we do know that yt is only depending on xt, correct? But in the other case, we don't know. Yeah? So you potentially could connect these guys to each other, right? But at the end of the day, the optimal weight for them is 0, meaning that you just cut them. Because if you put them next to each other, then you are learning from independent sequence temporal correlation, which doesn't make sense, right? Clear? Yeah? So you have a good feeling about the sequence being inside your data set right now? So a sequence could be very long. So when you talk about the sequence inside your data set, you don't potentially need to have 10,000 or 50,000 sequences anymore, right? Because the whole CFAR or the whole MNIST could be one sequence of a very, very long length, right? Clear? Yeah? Okay. So now, so as I said, your RNN, if you want to just now think a bit more generally, your RNN could be anything. The only thing that you need to add is to just make that connection between one of the hidden states and the input. So you potentially could use MLP, you could use convolutional layer, you could use ResNet. So you could put one ResNet and then take the output of, I don't know, one of the convolutional layers or one of the residual units and then connect it back to the input, right? In time, not skip connection anymore, right? In time, like when you see the output, you save it. Next time, you give it as the input, correct? So you can do it, and that's going to work. I mean, there are implementations like recurrent ResNet exists, recurrent CNN exists, all of them exist, but the most conventional ones that we usually start with always, and usually use it, like LSTM that you have heard of, they are usually considering fully connected layers, yeah? Because for many temporal, I mean, at least initial temporally correlated, like time sequences, the problem of like the learning target was not that complicated. It was a simple classification. You could do it with an MLP. You only wanted to just capture the, memory. So now, one, change them? Yeah, oh, okay. You might wonder, I mean, if we have one particular architecture, should we change that architecture or not? I mean, there are two key changes that we do in the architecture, but they are not like crucial. One of them is that we usually use tanh as the activation function. You're going to see today why we do it. It's simply because we're going to see vanishing over time, vanishing gradient over time. This is one of the things. And the other thing is that we're going to just modify our dimension at the input. And of course, you do understand it, because your input is going to also, in addition to your input entry, it should include the state, right? The hidden state. So, for example, as you can see here, I mean, here I'm just considering one shallow RNN. So this is basically the Elman model that we had before. And if we look at this guy, we're going to have a bunch of activation inside the hidden layer, right? So once you just do the linear transform, then you're going to activate them. And typically we do it by, I don't know, ReLU, sigmoid, something like this. But when it comes to RNNs, we usually do it by tanh. So this is one thing. And of course, we're going to modify the input of this hidden layer, because this hidden layer is going to not only include X, but is going to, also it's going to include the hidden state from the previous time. And you saw how we did it before, right? So one way that we can look at it, like in this shallow RNN, we can show it in this form. So this is the typical thing that I'm going to do from now on. So this is the easier way of thinking about things. So I'm going to just look at this guy. And this guy is the one which is going to be like the hidden layer, right? So it's going to be a bunch of weights and activation. And then I'm going to get the guy from previous time, my input at this time, and then I'm going to give HT, the next hidden layer, as the output. Clear? So this is going to be the way that I'm showing. Some people show it like that. I don't like this, so I'm not going to do it for you, okay? But it's just simply that the output, it gets delayed and get fed back to this guy, right? So I don't like it. I don't do it, okay? Now, you might ask, isn't that the Elman? This is basically Elman, but Elman used sigmoid. We don't use it. We are using tanh. This is one thing. And the key thing that Elman couldn't do is just training over time, which I'm going to do now. Okay? So Elman stopped when he just backpropagated down to this H, but I'm not going to stop here. Clear? Okay. So now you could potentially make your RNN deeper. If you want to have a very deep RNN, you should just, I mean, now you see you have some axis, which is here. This is time axis. So it doesn't have anything to do with the depth of your neural network, right? But you have here the depth of your neural network. So here is depth. Now, so here I have still a shallow neural network because I have only one hidden layer, right? Input, hidden, output is going to be depth 3. 3 is still, sorry, depth 2. Depth is still 2, so it's not deep, right? If I want to have deep, I need to have more hidden layers, right? And I can do it that way. So I can get one hidden layer, I compute the output. Once I have the output, I give it to the next hidden layer, the next set of hidden features, and then I compute my output. And now if I want to make it RNN, the thing that I'm going to do, I'm going to get the output of that one particular hidden time, and then, a particular hidden layer, and then delay it in time and fed it back to the hidden layer itself, right? And I could do it at every hidden layer. I could do it in some of them. I could do it at all of them, right? Doesn't matter. Clear? So this is the version that I'm going to use. Okay? I don't use that diagram anymore. So X at one particular time comes, the hidden state of the first layer at the previous time also comes, and then they both together compute the next, the hidden state of the first layer in that particular time instant. Then I give that particular time instant hidden state of the first layer, and the hidden state of the second layer in the previous time instant together to compute the next hidden state of the second layer. And then I compute the output. Clear how I do it? Yeah? So when you see I have a deep RNN, you mean depth in that dimension, right? So now this guy is a deep RNN. This guy is a shallow RNN. So you wouldn't say that I get this guy and train it, I don't know, for 100 time steps. So it means that I have depth 100. It's not the depth. You get it, right? Yeah? So this is just the time instant. Yeah? It doesn't have to do anything with your depth of the neural network. So if you want to just imagine the thing that we had before, which we always showed it horizontally, this guy has only depth 2, the next one has 3, and so on, right? Clear? Great. So now you can do lots of things with this guy. I mean, you don't need necessarily to have just every hidden layer to be connected to its previous value. You can, for example, do a skip connection over depth. So this is what makes it residual, right? So I'm going to just connect the input. I mean, once I computed the first hidden state, I'm going to get the input and then add it up to that guy and then compute the next guy, right? So why should I do that? Vanishing gradient. But vanishing gradient in which dimension? In depth. Great, right? So I could do this because I want to avoid vanishing gradient in depth. Meaning that if even my sequence is of length 1, I don't want to have small values of gradient, right? So one thing is that I can do, I can just cross-connect the time steps, different layers, right? So for example, I can get the hidden state of the other layer in the previous time step and feed it to my first layer in next time, right? I can do it. It's a bunch of state values. I can just get it, multiply them with a bunch of weights, and then add them up, right? And I can now go even deeper in time. Yeah? This is a different thing, right? So I don't only use the previous time step, but I use 2 previous time steps as well, right? And if I want to make it like connected to this time, I need to skip 1 time step, right? Now, this is a skip connection in time, and this is different from this guy, right? And you get the idea, correct? So it might initially sound complicated, but I think right now you have a clear understanding, right? Any questions? Yeah. Yeah.
So I guess I get the intuition behind each operation, but I just have one question: is that how effective are they overall?
I mean, at the end of the day, I mean, we don't really implement this skip over time. We do gating, and this gating is some implicit form of skip connection. So we do that. But how deep we go, you actually go deep. I mean, with LSTM, before LSTM and GRU getting like trend, people were just using basic RNN, and it was hard to just make them work. But once the idea of gating was somehow discovered, then people started to feel confident with that. And now potentially you can go deep. I mean, in PyTorch, you can just have multiple layers of LSTM.
So and then you can go deep, then it's better performance?
Better performance, yes. Yeah. Better performance, but the better performance is simply in terms of the classification, right? I mean, of course, they are interconnected somehow, but you could roughly just separate this depth dimension from time. So the time dimension is going to enrich you with capturing the correlation, whereas the depth is just making your model more strong to be able to just learn new, more complicated functions, right? There are 2 different things. Right? Yeah.
Yeah, so my question was like, I think it follows this one. So the skip over time helps with gradient vanishing?
Yeah, I mean, theoretically it could help, but we are not going to do this directly. So we are going to use gating because it's going to be very hard. And gating was there before all of these people were introduced. So. Any question? No question. Great. Okay, yeah. And convolution, of course, and any other kind of layer, you can just think of them as any of those kind of layers. So now, I'm not going to just complicate things for you, so I'm not going to open up CNN or recurrent CNN or skip connection residual recurrent residual network, because it doesn't really make sense. You do have understanding of every single one, and then you can just combine them. But to just see this new part of the story, which is learning through time, we are going to just deal with the very basic one, which is a shallow RNN, meaning that we only have one hidden layer. Yeah, and if you look at most texts on RNN, I mean almost all of them always consider that one. Once you understand this one, anything beyond that is very easy for you to expand. So this is basically the Elman equation, Elman network. The only thing that we want to do now, we want to just address the thing that Elman could not do it at that time. So now, how does it flow? How does the information flow in this network? So I have a sequence of length t, and this guy is, as I said, each of them could be potentially a frame. And then I start with one particular initial hidden state. So that hidden state is the memory component that I have. And I start with some initial values. So I just make one increment. So say everything 0 is my initial value. And then I give this guy to this hidden state. I also give my input to the hidden state and compute the output. Activate it, go for the output, right? Now, then when I want to go into the next time, so I still have my hidden state from the previous time, right? And I give that one, again, as the input to the same layer, right? To the same layer, plus the new input and compute the new hidden state, right? So you can think of that hidden state as a kind of box. So this guy is basically like one box, yeah? And then you initially start with H0, right? And then once you go for the next time step, you remove this H0, you fit it back to the same component, you give the input, and now you get H1, right? Right? So it's like what you do when you are coding. When you want to just have one particular variable in a loop, you are not saving every single entry of that loop, of course. You are just defining some H, and each time you are going to update it, right? It's the same thing happening here. Clear? Yeah? So this is what I'm going to do, and then I'm going to get the next one, and then same thing going to happen for H2, H3, and so on until I get HT minus 1. So if I'm at one particular time, I could say I have HT minus 1 fed into my hidden layer, XT fed into my hidden layer. Both of them compute the new hidden state, and then that guy is going to compute my output. That output is the thing that I want to see, right? That is not that crucial. The key thing now is just this hidden state, which is evolving through time. Correct? Okay. So that's it. So now let's first see in this shallow recurrent neural networks how many learnable parameters do we have. What are the learnable parameters? Can you tell me? One guy is, of course, connecting this input to this one, right? So we have a bunch of weights there, right? So we have a bunch of weights. Oh, I started from the output. So from the output, so say I want to compute the output, I have a bunch of weights which are going to get multiplied with the hidden state, right? And then I compute the output, right? So that red guys are learnable, correct? Every single entry inside W2 is learnable. This is something that I need to compute the gradient with respect to. Correct? Next thing. These two guys are again learnable because when I want to compute this hidden state, I am going to get some WM. So M stands for memory here. I'm going to get the previous hidden state. I multiply it with a bunch of weights. And then I add it up to my input again times a bunch of weights. So the green guy and the yellow guy, they are again learnable, right? Clear? Anything else we could learn in this architecture? Yes or no? No. Nothing else, right? So everything is like this, right? So every red guy is the same thing, every yellow guy is the same thing, every green guy is the same thing, right? Correct? So if I am at this time, and then I compute the gradient, and then I update my weight, now if I look back in time, all of those green guys have changed to this new value, correct? So you don't think that this is another bunch of weights, right? The weights are all the same. Clear? Yeah? Great. But you actually answered wrongly to my previous question, because there is one tiny thing else that we can learn. The initial state, right? I mean, there is no reason that we stick to one specific initial state, right? So I can again think of them as a bunch of, weights, and then I just update it each time, right? Maybe that's going to help. Clear? I mean, we usually don't do it, but we can. Yeah.
Can you say again how we learn the initial state, H0?
You just compute the gradient of the loss with respect to this one, and then you update it.
So H0 is the initial.
Yes.
It's not even a state because it's something.
It's initial state, it's something that you start with.
We don't start with that, right? We start with x1 and we compute h1.
No, but you need to have your h0 as well, right?
Okay.
So say, for example, ht is of size, say, for example, n, right? So it means this is one vector of this form. So it's h1 at time t, h2 at time t. I mean, till n at time t, right? And then you, for your time 0, you can think of them as being a bunch of weights, right?
Yes.
And each time that you are computing, you can compute the gradient of your loss with respect to them, meaning that the partial derivative of r hat with respect to every single hi at time 0. You can compute it, correct? And then you can simply just update them every time that you are updating any other weight.
We are updating H0.
Yeah, because H0 and every other guy in this diagram, every other weight, all of those matrices.
The H2, H3, they will be updated.
H2, no, they are getting automatically updated. You cannot compute the gradient anymore. I mean, you can compute the gradient, but you have nothing to update, right?
So this gradient from risk to H0 is going to be gradient vanish, no?
This could potentially vanish, right? This could vanish, yeah.
But over time, after we compute H1, we compute a derivative of 2H0 and we update that.
Yeah, we can update that. So the thing is that you're going to get your, this is your data set, right? Yes. So you have x1 to xt all there, right? Everybody stands there. And for those guys, for the moment, you can think for every single time instant, you have the true label as well, correct? So you start with one H0, one choice of H0, and one choice of all of those weights. You just go all the time, all the way into the time, right? Now that you are here, you can compute your gradient of the loss at the very output, average over time, with respect to every single guy in this architecture, all of the weights and the input, right? You update everything, you again start from time 1, and then you go to the end. Then when you are over at the end, you again compute a new gradient, and then again you update, right?
I see.
And you keep on doing it till you see what you want to see.
Initial was H0. I see.
Yes, and you're going to keep doing this. Each time, if I just do one back propagation and compute gradient with respect to H0, then the next time, the next iteration that I want to compute the gradient, I need to go forward, right? Yes. And I start with that updated H0 now. And I go all the way to the end, right? And again, I compute the gradient, and I update. Yeah? And again, start from the same time. So each time, so each of your iterations is just going over time t times, right?
Yes.
You get it, no?
Yes.
So you don't think that they are really coming on the fly. I mean, when you use it in future, when you trained it and you use it in future, all of those X's could come on the fly. But when you are training it, you have the whole sequence. I mean, if you don't have it, you cannot train it, right?
Yeah, because the whole sequence is capped at capital T.
Yes, exactly. Yeah, you have lots of sentences, each of them of some length.
But they will be less than capital T length.
Yeah, I mean, if you agree. I mean, this T could change from one sample to another,
Yes.
potentially, right? But when you want to train, say you have just one sample that you want to train. You have the whole sentence, right? You put it here, you're going to see at the output at every single time, and then you see they are not the next words, right? Then you are going to compute your gradient with respect to weights and initial state. You update all of them, and again you start from the beginning of the sentence, you look at the output, you say, okay, it's no better, but still it's not exact. I mean, every single of them is not exactly the next word, right? And you keep on doing it until you see every single output is exactly the next word in this sequence that you have for training, right? And now you hope that if you now give a new sentence, it's going to give the next word.
Yes.
Yeah?
Makes sense.
Clear?
But in practice, we will have many samples. So we will have like
Yeah.
one average over gradient, and the gradient will be like over many times.
Yes, I mean, it depends on the application that you have. I mean, you could potentially have one sequence like when I tried to explain like the previous guys, previous problems were a special case of this one. So you could think of, like in MNIST, you could think of one-to-one problem, but then you have a sequence of 50,000 samples, right? Entries, sorry. Yeah? So you could have one sequence which is hugely large, right? So you have a textbook, yeah? You can look at the whole book as one sequence, which is huge in time, or you could just look at it as a bunch of sentences, and then each of them is one sample, right? Both of them are possible. And it totally depends on your problem, right? So if it's a text inference problem, probably it's a better idea to break it down into sentences, right? But if it is a very new problem where you really need to just capture everything from very, very beginning of time, then it might be a better idea to just go the whole way to the end of the time. And then the question is how capable you are to just backpropagate all the way back to the beginning of time, right? So given your computation, the kind of application that you have, you could have just a few sequences in your data set, very long, or you could have lots of sequences not that long, right? Yeah, but it's good. I mean, it's practical to think of having like thousands of sequences, exactly. And then you average over all of them, of course. Yeah.
So how is this different than just training the Elman network then?
Yeah, the difference is that Elman did not go to the beginning of time, right?
Oh.
And we are going to do that, and we're going to see that the gradient is vanishing, and then we try to find a remedy for that. Yeah, okay? Any questions? So what is the next guy? Oh, training. So let's have 5 minutes break, and then we start training them. Uh-huh. But it's going to be very short training this time. Okay. So, shall we go on? Okay, so now the thing as I said, so this is basically the L-man architecture. The only difference is that we now want to train it over time. And it could be a bit of hard thing to do. So one thing that I'm going to just assume at this moment is that I assume that I do have or I do know the sequence of the true labels. Okay? So as I told you, the sequence of true labels, it doesn't mean that we have one-to-one mapping, right? One-to-one correspondence. It means that it could be also like many-to-one case, right? So every single y here is not really corresponding to one particular label. You get the idea? So, but what I assume that I can make up some labels. We're going to deal with that issue later on, okay? So you could assume that I have, for every single guy here, the particular label. So I do know what should be exactly V1. Yeah? And if you want to think of those, general cases, you could think of V1 being simply empty, right? If you want to have only one output, so V1 to VT, the VT minus 1, actually the one before the last, so they're going to be all empty, and then you have only VT, okay? So that is an issue. Also, the same thing is going to happen with XTs. So XTs could also be potentially, some of them could be simply empty, because, for example, we have one-to-many case. So the first guy goes in, and everybody else is simply empty, right? But it's not going to harm our problem, because at the end of the day, we really don't need to compute gradient with respect to input, right? We only need gradient with respect to those, weights, and it's not going to harm the analysis, okay? Great. Now, one thing that I'm going to do, now, last time when I wanted to do this for you, I saved the good chunk here, no? So I told you that the loss that I want to compute, this r hat, if you remember, I just wrote you that this to be summation of t from 1 to t, loss of Vt, Vt and Yt, right? So I did it like this for you last time, correct? But this is not necessarily the good idea, okay? As we're going to see. Now, what I'm going to do from now on, I'm assuming that this loss is a kind of more general function which could get the whole sequence of the outputs and the whole sequence of the labels, including those empty labels, and then it could compute us the loss. Then we'll later on see how we can define it, okay? That is the CDC approach, okay? Now, since I have this, now I can look at my forward pass in this form. So I start from the first time, I just go over the whole time to the very, very end. Now I have all the outputs through time. And the thing that I'm going to do, I'm going to give everybody into one loss box, right? One loss function. And that loss function also gets all of my labels, and then it can compute r hat, right? And then since you don't know what exactly that loss is, you might wonder whether we could get back from loss to those, outputs. For the moment, I assume we can. Meaning that if I compute, I just go forward and everything is over, then I'm able to just, here. Okay. Then I am able to just move backward to everybody here, right? I can compute the gradient with respect to every single one. So I do now, so I told you that I'm not going to show it anymore like this, because it's very special case. It might be the case that we cannot do it. I am going to write it down in this form. So I'm writing it to be the loss, y from 1 to the capital T, the whole sequence, and v from 1 to capital T. And what does it mean? This guy is y1, y2 till yt, right? And these guys are fixed. So I don't care about that. And I am able to compute the partial derivative of this r hat, or the gradient of this r hat, with respect to every single yt that I have here. Okay? I can compute gradient with respect to y1, y2 till yt. Okay? Clear? Now, if I go forward, I end up computing the empirical loss, then I could just move backward to those outputs, right? And the whole thing is start from this point for us. Clear? Great. So now, if I want to, for example, compute the gradient with respect to one weight, yeah? And for the moment, you just think about the shallow RNN, right? So we are talking about the shallow RNN. Clear? Meaning that WM is this guy. What did I? Oh. So I found, it turns out that, these are the high quality chalks, and everything else is low quality chalk. So I just found this, remained from one other lecture, so it's like gold now, okay? So I'm just...
Put it in your pocket.
Yeah, but I don't want to make it worse than that. Yeah. But, yeah, this is WM, right? Clear? So I have this WM is getting multiplied with this guy, computing my, plus this guy, which is W1, and then this guy is going to go for the next layer, so this is HT, and then this guy is W2, correct? Now, I want to compute the gradient of the risk, which is the loss, this guy, with respect to this WM. Clear? Yeah? And one thing, here again, I am assuming that I'm dealing with only one single sequence inside my data set, right? But you do know why I do this, right? Because at the end of the day, if I have a mini batch, I'm going to average over them all the stories as before, yeah? So I do not need to repeat it. You know that if you can do it for one sample, you can do it for the whole data set. Training is over, right? Okay, now I want to compute the gradient of this R hat with respect to WM. If I want to do that, what should I do? Of course, I should do chain rule. What is the first chain rule I should write?
W2, the gradient to W2.
Yeah? So first, I should go for what? This R is a function of y1 to yt, correct? So I need to get back to all of those outputs, and then from those outputs, I go to W, correct? So it means that I'm going to write the gradient of R hat with respect to y1, for example, and then I multiply it with some sort of multiplication with what? The gradient of, you tell me? Y1 with WM, with respect to WM, exactly, right? Now, should I stop here? No, I should keep on going. So what is the next one? Exactly, y2 R hat times the gradient of y2 with respect to WM, and I keep on going like this, right? Clear? So I write it down in this form, so I'm just going to write it, start from the first output to the output at time t. I compute the gradient with respect, I assume that I can get back, so I do know these guys. These guys are known to me. These guys. I assume that I can get back to the output. Yeah? You don't exactly know how right now, but you're going to learn it. Okay? And then after that, I need basically to compute the gradient of every single output with respect to WM. Right? So just write it down in form of a summation. So now, this is, first of all, let's see what kind of object is that. Right? So what kind of object is it? That Ym, this is the output of the output layer. I told you it's a vector, right? So this guy here is going to yt. And this yt is potentially a vector. When I say gradient of yt, any t, with respect to Wm, what do I mean? How does this guy look like? This one? It's actually beyond the matrix. It's a tensor, great. Yeah? Because this guy, y1, is y1, this y1, you think of y, or yt in general, you think of it as y1t, y2t, and so on till ynt, right? This is the guy, right? When I want to compute the gradient of this guy, what should I do? I should compute the gradient of every single guy and put it in the same array, right? If I compute the gradient with respect to one weight matrix, what kind of object are every single guy here? It's not the Jacobian, because the output is not every single entry is not, this first entry is not a matrix anymore, right? It's not a vector anymore, right? What is it? It's a matrix, right? So it contains the gradient of that particular entry with respect to every entry inside the weight matrix. Clear? So this is the same size matrix as W itself, right? And then you put lots of them next to each other. Now you have a tensor, right? So this is the guy. So you see, the first entry, you compute the gradient, it's a matrix. You put it next to the next matrix and so on till the very end one, right? The very last one. Clear? So lots of matrices next to each other, it's going to make you a tensor. It's going to make this story a bit complicated, right? So it's going to be exhausting if I want to go backward, but we have no other way. We have to go, right? So that's it. No, I'm just going to get the help from my very close friend. Yeah? So we're not going to just you do get that everything is now tensor-wise more complicated as before, but I don't want to do that because this is simply just computation for you. Okay? So the thing that we are going to do, we are just going to focus on a very dummy one. Okay? Like what we did in this skip connection. So we assume that every single guy here, these y's, those weights, everybody is a scalar, right? And all of those gradients now are simply derivatives, and then you don't need to think of tensors, other things, right? Clear? But of course, in your mind, you can always extend it to the general case, right? And in practice, PyTorch is going to do that for you, right? Clear? OK, great. So now what I'm going to do, I'm going to think of the hidden state to be one variable. So this guy, for example, gets multiplied with just one weight, and I compute the output. Again, I am going to just consider the input to be a single number. Since the hidden state is also a single number, I'm just going to just do this superposition, and then again I compute one scalar number. Clear? No bias, nothing, just simple weights. And we have hidden state H0, meaning that we start with one number here, you compute that function, you're going to get H1, feed it to the next layer, and so on till very end. Clear? Easier problem. So now, what we want to do, we wanted to compute this gradient of one of the outputs with respect to the weight matrix, right? And now here it's going to be a simple partial derivative, correct? So I'm going to compute those gradients. And the first thing that I'm going to do, let me see. OK, the first thing is to just go forward. So I assume that I have done the forward pass, of course. And I computed everybody. So I do have every y, h, everything. You do know that. So it was just for sake of consistency. And then the first thing that I'm going to do, I am going to compute the gradient of the derivative of y with respect, when I want to do that, I'm going to go one step backward. Because let's get back here. So how does my y look like? So my y, I don't need that one really. So my yt is simply activated version of w2 times ht. And my ht is activated version of w1 times xt plus wm times ht minus 1, right? And now, the first thing I want to do, I want to compute the derivative of yt with respect to wm, right? And how can I go backward? Just look at this yt and tell me what guy is going to carry something about wm in it. ht, right? So the first thing that I'm going to do, I'm going to just write the chain rule with respect to ht. Yeah? So how do I do it?
Derivative of y with respect to ht.
Exactly. Wm that I want, right? Okay. So this is going to be the term, right? And you do know how to compute this guy, right? This is simple. You have y, right? This is y. Derivative of this guy with respect to ht is going to be derivative of this guy times the derivative of argument, which is w2, correct? So it's going to be w2 times f dot, the same thing.
One question: why is there a particular reason why don't we compute derivative of yt over w2 first? Because it seems easier.
Because at the end of the day, I'm looking for the derivative of loss with respect to Wm. I mean, I can do it as well, but that's going to stop here because that W2 is not going through time, right? No, my main purpose that I look into Wm is because it's the hard one. I mean, W2 is very easy. It's the same as before, right? You stop. No. So, now, I can compute this guy, so this is going to be this one, so I'm going to replace it there. And now the next thing that I want to compute is the gradient of, or derivative of ht with respect to Wm, okay? Now, one thing that I'm going to do, I'm going to look at ht with respect, this guy is ht, correct? This is ht. And I want to compute the derivative of this one with respect to Wm, okay? Now, this guy is an immediate function of Wm, of course, but this is not the only thing here that depends on Wm. What else we have? ht minus 1, right? So, like last year when I did it, some student got confused because when I start to write down the chain rule, it's going to be the derivative of ht with respect to Wm is first derivative of ht with respect to Wm plus something else, right? Which people started to find it weird why something should be itself plus something else, right? So to avoid this, I'm going to use this notation. So I'm saying that ht is a function of Wm and ht minus 1. Clear? Right? So I am saying that ht is a function of Wm and ht minus 1, correct? And then this guy, you do know what that is, right? It is activated version of W1 xt plus Wm ht minus 1, right? And I am going to call this guy, I save it for later, so I'm going to call this guy to be, the worst color, zt, okay? We're going to use it later, okay? Now, if I want to just write down the chain rule here, it means that I want to compute the partial derivative of ht with respect to Wm. How can I do it? Maybe you can help me so that everybody is now fresh. Derivative of ht with respect, or g with respect to Wm times derivative of Wm itself with respect to Wm plus great times ht minus 1 times Wm, right? Correct? Great. Now, this guy, this one, what is it? 1. Great. Okay? So then it's going to be like this. So this guy is 1, correct? And the next guy going to stay there, right? So I just defined this g because if I do that, you see this derivative of ht is derivative of g with respect to Wm times that one. If I don't write g, I immediately write ht. Then you're going to see derivative of ht with respect to Wm is same thing plus that. So some people find it confusing. But I hope that you get it clear now, right? So by this term, I simply mean the immediate derivative, right? So I think of ht minus 1 at that point to be constant. Clear? Right? Great. So now, zt is this guy inside the argument, yeah? And my ht is simply my ht. is simply f of that zt. So it means that this g function that I'm looking for is basically f of that zt. And then you can go ahead and compute that derivative. So maybe we do it again together. So it's going to help a lot getting out of, tiredness. So what's going to be the derivative of g with respect to Wm? Can you tell me? If I want to compute the derivative of this guy with respect to Wm, it's going to be ht minus 1 exactly, the derivative of the argument, times derivative of the whole thing. So it's going to be f dot of, I'm not going to write down that term anymore completely, so I'm going to write it down zt. Okay? Clear? What about the derivative of g with respect to ht minus 1? What is it? It's the same thing, right? Instead of ht minus 1, I'm going to have Wm, right? Because the derivative of the argument is with respect to ht minus 1 is Wm, and then everything else is the same, right? So it's going to be Wm times f dot zt. Clear? Right? Everybody's clear?
There's one more thing. The derivative of g over derivative of Wm
Okay.
is so Wm is affecting g by ht minus 1, but within ht minus 1 there is more Wm.
This is the thing that I didn't want you to get into.
I confused in the way that previously was done.
No, yes. Yeah, I know, this is confusing. So when I write derivative of g with respect to Wm, what I do mean, so look at this guy. G is a function of these two guys, right? And then when I say partial derivative of g with respect to this one, this means that I don't care how it is changing. I'm going to look at it as a constant, right? And then that effect that you say is going to show up when I just get this next term. Clear?
It's like the difference between the explicit derivative and the total derivative.
Yes, exactly. Yeah, this that I write here is explicit, but then the total is going to be this one. Yeah. So you are thinking of the impact of dependence of ht minus 1 on Wm. So it's going to show up here because I get the derivative of that one with respect to ht minus 1, and then I multiply it with ht minus 1 with respect to Wm, right?
So we split that in these two terms so that the recursion doesn't happen.
Yes, it's going to happen. So I'm going to show it. But just to make it clear for you, when you have g of x and y, so this is your h, right? When you want to compute derivative of h with respect to anything else, so with respect to some w, what you're going to do, you're going to take explicit derivative of g with respect to x, right? So it's going to be the partial derivative of g with respect to x. And then you multiply it with partial derivative of x with respect to w. And then you add it up with the partial derivative of g with respect to y times derivative of y with respect to w. Clear? This is the same thing that I'm doing, right? So y for me is ht minus 1. X for me is w itself, right? So if it is confusing for you, instead of having, I put here w, right? Wm. But instead of Wm, you could, for example, write it down here another function. I don't know, gamma. Yeah?
Let's do Wm.
Yeah, just to make it. Then it's going to be derivative of ht with respect to Wm. It's going to be derivative of g with respect to gamma times derivative of gamma with respect to Wm. And the next thing, right? And then now this one is going to be 1. Clear? You got the idea? Okay. Great. So, yeah. Now, we have these two derivatives, and then I can just replace it in that equation. Clear? So I'm going to find the derivative of ht with respect to Wm in terms of everybody else. Yeah? So this is going to be the case. So basically, I have f dot times ht minus 1. This is the first term. Yeah, this guy goes here. And the second term is the same f dot, but this time is multiplied with Wm. Clear? Clear? And then I also have here, as you can see, ht minus 1 with respect to Wm. And this is going to show up here. Clear? Everybody's cool with that guy? Yeah? Great. So now, if I get into this point, what should be the next derivative that I need to compute? Derivative of ht minus 1 with respect to Wm, right? But you can see that we do already have the recursive form, right? So I have the derivative of ht with respect to Wm in terms of zt ht minus 1 here, right? So when I replace ht minus ht here with ht minus 1, it's going to be zt minus 1, ht minus 2, right? And you keep on going backward in time. Clear? So if I want to do the next thing, again, you can look at it as before, and then you could say that, okay, if I replace ht with ht minus 1, then zt going to be zt minus 1, and ht minus 1 going to be ht minus 2, right? And you keep on going backward like that in time till you arrive at the beginning of time. Everybody's clear? You got the idea? Great. Now, at time t, if I want to compute the gradient of the output with respect to the memory weight, I have this term, and then I can just recursively start from time t, and then each time I just go backward to compute the next gradient of h with respect to Wm, right? So I start from time t, I compute the gradient of ht with respect to memory weight in terms of the gradient of ht minus 1 with respect to the memory weight, right? And then for that one, I again compute that gradient in terms of the gradient of ht minus 2. And for ht minus 2, I computed ht minus 3. And I keep on going till I get to the very beginning of time, which is h0. And at that time, there is nothing behind anymore to backpropagate, so I stop. Clear? You got the idea? So this is what we call it backpropagation through time, right? So I just start from one time t, I just go backward till I get to the very beginning, and that time I stop. As I said, this is the backpropagation through time, so it means that I start from this time, I come here, and then I just go backward from each of them. I just go backward to the previous time. But the cool thing about this backward propagation is that at each time when I want to go backward, I'm just doing one recursion, right? So it's not going to be a new term, right? So it's the same term, I just need to compute it for the previous time instant. Clear? And then you can simply understand now, I guess, that you start from very beginning, you go towards the very end of the time, and now when you are there, like you just need to start from the very last yt and go backward to the very beginning, right? And once you went there, everybody else is going to just be computed based on those computations, right? You see it? Clear? So you basically do one recursion over time till you get to the very beginning of time. So, for example, say I am at particular time t, and I want to compute the gradient of yt, this particular t, with respect to Wm, to the memory weight. So I'm going to write it down in this form, and I do need to know what is this gradient, right? Gradient of ht. But that gradient of ht, if I want to know it, I need to know a gradient of ht minus 1, ht minus 2, ht minus 3, till h1, right? Correct? I need to go up to that point. Correct? Everybody's clear? Okay. So if this is the case, so at time t, I'm going to go all the way backward to the beginning. Now if I go for time t minus 1, I'm going to have the same term above, but instead of t, it's going to be t minus 1, right? And if I want to compute the gradient of yt minus 1, I need to know the gradient of ht minus 1. Do I know it? I already know it, right? Because I computed it before, right? When I wanted to compute the gradient of ht, I did compute the gradient of ht minus 1, right? You got the idea? So Once you go all the way to the end of the time, then you just go backward to the beginning of the time, and then that's it. Back propagation through time. Clear? Okay, so you just, moral of the story, you just pass forward to the end of the sequence, and then when you are at the end of the sequence, you just back propagate all the way to the beginning of the sequence, and then that's it, right? You have what you need. Yeah. It is in some sense time consuming because you are potentially doing a very deep gradient over time, of course.
But for example, right now we can see the caption of videos online, on time.
Of course, yeah.
And is it with deep learning or another?
Yeah, they are with deep learning. I mean, they use transformers.
Yeah.
You can do ideas. I mean, as I told you, we're going to see gating. So it's going to help us. But again, when you do gating, you just go all the way back to the beginning of time. That's correct. Potentially, in some application, you could say that I'm going to truncate it because at some point I do know there is no useful information anymore. But there are also, I mean, even when you do that, as we're going to see in chapter 7, it might be that it doesn't work because you do so much back propagation through time that you just lose the sense of the importance. And this is why we do the attention method, okay? So we again get everything here, we just feed it into another neural network or another layer, and then we keep some attention components, which going to help us when we want to backpropagate. It's going to tell us like attention to this particular time moment. Yeah. So there are lots of remedies for that, but in practice, like if you are just implementing a simple LSTM, of course, you just go all the way back to the beginning of time. And your sequence could be of the length 1,000, even more, doesn't matter. I mean, the gradient usually is not that complicated. That particular gradient that you are moving backward in time is not that huge. Yeah. So, any questions? Everybody's clear? Okay, so this is backpropagation over time, as I told you. If you're at time t, then you need gradient of ht. And gradient of ht, you can always find it recursively, right? So for any hi, you just need the previous time instant. And you just keep going backward till you stop at I equal by 1, where you don't need to just have gradient of h0 with respect to your weight, because h0 does not depend on your weight. Clear? Everybody's happy? You don't seem to be happy? I mean, you got over with the hard part. Should be happy. Okay, great. So now one question that you might ask is that, I mean, you already asked a couple of times, so this is going to be very deep in time. And potentially, it could make your gradient to vanish. Yeah? And this is correct. This is going to vanish. But the kind of vanishing you see here is a bit different to the vanishing that you had before. But still, it needs solution, okay? But before we just come with the solution, which is the gating principle, we first need to get a bit of sense about what does the vanishing in this backpropagation through time mean. So we are talking about this guy, so maybe you go ahead and put all of those equations that we computed right now nested into each other, okay? So you start with this term, and then, I mean, you start with this term, this finite gradient, or maybe this one, and instead of this gradient of ht, you really go ahead and replace, yeah, ht minus 1 into it, ht minus 2, and so on, you put it, right? If you do that, I mean, just look at this term. If I replace ht here, this gradient, with this argument, what's going to happen? I have one term plus another term, right? The first term is not going to change anymore. The second term is going to depend on the gradient of ht minus 1, right? And then again, ht minus 1 is going to be one term plus another term, right? When I replace it, it's going to be another term plus a term which depends on ht minus 2. And I keep go backward, right? Clear? So you're going to see that I have t different terms added up to each other, correct? So I have opened them up for you here, so you don't really need to compute anything. So this is the case that is going to happen. So this is going to be the first term that you're going to see. So your gradient with respect to yt is going to be the first term times ht minus 1, right? And then you're going to have plus another term. You forget about all of it. I mean, you can just replace those recursive equations to find it. But it's now times ht minus 2, right? Clear? And then the next term going to contain ht minus 3, and you keep on going till you get into h0, correct? Everybody is following?
Sorry.
Yeah.
From the first line to the second line, which has been expanded?
Now, they are some, you know. You pay attention to that. Yeah? Yeah? So what you are doing here is that, I mean, where is the good guy? Oh, here. So, yeah, I have this one, right? So this is this guy, correct? So if I replace it, it's going to be ht minus 1 times f dot of zt, right? Plus, again, I have f dot of zt times wm times this gradient, right? Gradient of ht minus 1 with respect to wm, correct? And then I again replace this one with that summation, right? So it again going to be ht minus 2 plus something else, right? And then I multiply this one to ht minus 2 plus another term. And I open them up all the way.
That's how the recursion.
Yes, exactly. Recursion, I mean, it's just a telescopic expansion, right? Clear?
Yes.
Okay. Now, what is happening here? So let me just simplify everything for you here. So you just focus on those ht minus something, okay? What I can say that the gradient of yt with respect to wm, that guy is one term. I'm going to write it down, for example, alpha 1 times ht minus 1, correct? Plus alpha 2 ht minus 2. Clear? So what is alpha 1? Alpha 1 is w2 f dot f dot. What is alpha 2 is w2 f dot wm f dot f dot. Right? You see it? Clear? So plus so on till, for example, alpha I h of t minus I. Right? And I'm going to go all the way back till the last term, which includes h0. And what should be the coefficient here? Alpha t. Great. So it's going to be alpha t, right? So I'm going to have t different coefficients computed in terms of everything I had in the forward pass, and then I multiply them with the hidden states, right, over time. Clear? Everybody's clear? Yeah? Great. So I have this guy, and when I am updating my wm, okay, I get this one and I update my wm. So my next wm is going to be the previous one minus my learning grade times, of course, r hat with respect to wm. And this one, we already wrote it down as yt times gradient of yt with respect to wm, right? Correct? So this guy, when it's getting updated, is getting some impact from the previous time step, right? 2 previous time steps, 3 previous time steps, so on to the beginning of time. So all of them are contributing in this update, and it makes sense because we want to carry the memory, right? So many of you had doubts about this memory over time that we talked last session, but you can see it right now that when I'm updating, everybody is showing impact, right? Now, let me look at one particular alpha I here, okay? How does this alpha I look like? So this alpha I is going to be of this form. You see it? So it's going to be multiply of lots of derivatives and weights, right? You see it? Everybody's clear? Yeah? So you just copy what I did here, and then it's going to be this one. Okay? Now, could it vanish or explode? Yes. Yeah? Because I have lots of those derivatives. And we know that if those derivatives are very large, then multiply of all of them, it's going to explode. If we have lots of small derivatives, they're going to vanish, right? Okay. So, but what does it mean? Does it mean that my gradient is going to be 0? No. Great. So, what's going to happen? I mean, alpha 1 obviously is not going to vanish, right? Because for alpha 1, I have just one of those derivatives. It's not going to vanish. This one is going to get a bit smaller, but again, I don't expect it to vanish, right? When I go very deep in time, then they start to vanish, right? Clear? So this guy is going to get close to 0. The next one is going to get approximately close to 0 till the last one, right? So you still have gradient. That gradient is not 0, but that gradient does not include those extra terms. Yeah? Those extra terms are getting 0, right? Now, this is what we call it the vanishing of gradient over time. And this is conceptually, the same thing as we talked in chapter 5 when we talked about residual networks. But the difference here is that when I implement this guy, I'm not going to see it in my implementation immediately. So I don't see my weights not getting updated. They are getting updated because my gradient is not 0. But the key issue is that my gradient is not carrying information of very past time, right? The information of a long time before is just getting vanished in my gradient. Clear? Everybody got the idea? So, now, is it a good thing or a bad thing or neutral? It depends, but in general, if you want to speak.
Because the very old memory just gradually fade away.
Exactly. Because we initially, you just remember the dummy example I had, Yulia and then some sentence, her. Yeah? So I just want to keep fresh memory of Yulia, correct? So if that Yulia is always getting multiplied with some weight, which is vanishing, as I go through time, the impact of Yulia is not going to show up in my gradient, meaning that my weights are not getting updated with respect, proportional to Yulia properly, right? And then at some point I'm going to forget. Yeah? This is what we call it lack of long-term memory in RNN. So you don't have long-term memory in RNN because your gradient doesn't let you to carry it on, right? It's going to vanish, and all of old memory is going to get removed from your gradient, right? So this is what we call it a vanishing gradient through time. So, or there is no long-term memory in your RNN, and this is the key issue in RNN. But as I said, though it's conceptual the same thing as the gradient vanishing in depth, but it shows up with different outlook, right, in your training loop. So you still have gradient, but that gradient is not carrying information about a long time ago. So now you might say, okay, should we use the same remedy as before? Should we use, for example, skip connection? And my answer is yes or no. So if you ask many other colleagues, they would say no, yeah, but because we should use gating. But once we go through gating, we're going to see gating is basically again a skip connection. Okay, so we at the end of the time we use pretty much the same idea, but in a different way. Why we do it a different way? Because it is easier to implement, and it got implemented long before people start to think about skip connection. Okay, and that is the idea of gating. So there were, before the gating getting introduced, or was introduced, being rediscovered. So there had been two different approaches that people started to find out. Okay, one of them was the tanh activation. So what they found out was that if you put those f functions, those activations that you have, to be tanh, yeah? The activation that you use in your hidden layer. If you put them to be tanh, then it turns out to, the vanishing impact is going to be less crucial, okay? So you can carry more memory through time, okay? You can try it at home by just writing down that dummy example and try different activation, and then you see when tanh is happening, that slope of decay is going to be smaller, just short. But this is going to help you for a bit of extending over time. It's not going to do that much, okay? So this was the first thing. The other idea was the idea of truncated backpropagation. And that means that you just start from beginning of time, you go up to some time, then you stop, you don't go any further, then you compute your output, you backpropagate, you update everything, right? So now you're not vanishing because you just look at the small bunch of time slots, right? And then once you update it, you do know that your weight carries some information about the every time before, right? And then you go forward, you do it again for the next chunk of time frames and so on, right? So this was again a bit of help, so it could improve the training of your RNN, and you could carry some sort of memory from beginning towards the end. But again, this is not essential, so it's not going to just completely get rid of that issue, or at least partially, or say dominantly reduce the impact of gradient vanishing over time. Yes, you want to?
Is this because, so the tanh activation is because the derivative at 0 is 1 instead of 1/2 or 1/4?
I think so, yes, I think so. But you can do it numerically as well. Just try to have this dummy neural network that I showed you, and then you just go over time, compute those alphas, and then you just plot alpha against time. And then you're going to see that, like for ReLU, I think, I cannot say for sure for ReLU, for sigmoid you're going to get worse. So it's going to just vanish very quickly, but with tanh is statistically the best one. Yeah? But the main idea is the same thing, because that f dot is happening quite, it's going to carry more information, like it's closer to 1, of course, most of the time. Yeah. So, now, these two ideas were the key ideas up to some point, till people started to talk about gating approach. Yeah? And gating approach is the most sophisticated idea that you could do when you want to carry information. This idea was not introduced like when people saw this vanishing, right? Because, the idea was the master thesis of Schmidhuber, I think. Schmidhuber he was a master student in Munich. And then he did this like, I think, 90-something, yeah? And then he came up with this idea. He didn't call it gating. He called it LSTM, long short-term memory, okay? And then he said, like, if you do that, then I have the feeling you're not going to get rid of your long-term memory, right? And then nobody attentioned that idea because people were saying, come on, RNN is not working. What are you talking? It's a simple master thesis. People just do, and that's over. But at some point, people started to see that, okay, RNN is working. Maybe we can truncate and anything. And the supervisor, he just get back and said, come on, my master student did that. And they just implemented, and they saw that it's working. Then they tried to understand what this guy has done. And then they came up with the fact that he's doing something that they started to call it gating. And then LSTM itself was quite complicated, so they came up with the idea of gated recurrent unit, GRU. And GRU is the simple version of LSTM, but was proposed long time after LSTM. And they said, like, okay, let's just do it for a simple thing, GRU. And then they tried it. They say, oh, it's working, and this is really gating. And it's a sort of implicit skip connection through time. And they say, okay, that guy was actually doing gating. So now we have gating principle. And the first thing is GRU, which is very recent. And the more complicated thing is LSTM, which was proposed long time before. Okay? So the historic